interact with remote objects or virtual objects. Now, there is another important question that the field of haptics needs to answer, and this is how we can use the technology to create experiences. So this is right now very difficult. And so I want to give you an example of Eric. Some of you may know him. He's a PhD student with Catherine. So right now he's at Max Planck, and he's in his final year. Through the last few years, he has learned a lot. So he has created a device that can render touch sensations on your fingertip. On a daily basis, he programs this device, and both the programming and the design of the hardware needs to be based on the understanding of human touch capabilities. And so he also runs user studies. And so this is very typical of the type of tasks that someone who wants to use haptic technology need to do. So they need to understand haptic hardware, programming, and the perception side. So this is a lot. And as a result, the field is very specialized. And right now, only experts can create haptic sensations. But if you think about it, there are lots of application designers and domain experts who might want to use haptic technology to create new experiences. So for example, creating a multimodal application for education or improving surgery, robot-assisted surgery. And there are billions of end users, and with any technology, they have different needs and preferences, and they should be able to adapt it to their needs. And right now, we are not supporting end users and interaction designers well, and the field is even difficult for experts. Another problem is that these different groups of users are largely working separately from each other. They are disconnected, and they don't share information. Now, let's compare this to a more mature field, such as visual design. Their application designers have tools such as Adobe Creative Suite to create beautiful visual designs, and end users have tools for editing their colors and their photos, videos, and so they can create a lot of content. And so a lot of information is also transferred from experts to these end users and application designers through guidelines and templates. So the goal of my research is to make haptic design closer to where visual design is right now. And specifically, I'm interested in creating a future where anyone can understand, access, and adapt touch technology for their needs. So to do that, I studied a mental model of different groups of users. I create shared resources and collections for them to access the technology and understand it. And also, I investigate tools and algorithms that allow these groups of users to basically create and personalize their haptic experiences. So, and this is increasingly important because haptic technology is entering the market. So right now, there are over 27 companies around the world who invest in haptics. 13 of these are large companies, such as Apple and Facebook. And there are at least 14 startups. And 17 of these companies started working in this area within the last 5 years. So this is an exciting time for the field. The technology is starting to enter the market, and we need to be able to give people tools to control the technology. So today I'm going to talk about 6 projects. 3 of them are in the area of tactile technology and 3 in kinesthetic technology. So starting with tactile technology, where I spent my PhD on it, I focused on vibrations because this is the most widespread and accessible type of haptics. And I used C2 tactor, this round purple actuator. It's kind of like a high fidelity actuator. You have a lot of parameters that you can control. So you can create lots of patterns. Later in my PhD, I studied whether the patterns that we create on C2 tactor can be translated to lower fidelity actuators, such as the eccentric rotating mass actuators that we have in our cell phones. So the topic of my PhD thesis was personalizing haptics. This work is done at University of British Columbia in Canada with Karen McLean. And it's resulted in a number of publications that I'm going to overview in this talk. So the goal of my research was to create mechanisms for end users to personalize their haptic experiences. And so we are increasingly having tools for experts, but these tools don't work for end users. Because experts tend to think about technology in terms of engineering parameters that they can control, such as frequency, amplitude, waveform. But end users think about the same sensations very differently. So they think this is rough, this is strong. So there is a gap in the mental model of end users and experts. Now, this is not surprising. For example, for colors, vision experts think about them as RGB and wavelengths, whereas end users have names for them. So this is bright, this is yellow, this is warm. But despite this gap in their mental models, end users have tools for personalizing their color experiences. So I got inspired by color tools, because with colors we have a suite of simple and effective tools that are all built on a rich underlying theory, the color theory, and they could easily be incorporated into various applications that we use every day. So my goal for haptic personalization was to create a suite of tools that are built on one underlying model based on how end users think about haptic signals, and these tools should be easily incorporated into various workflows of end users. So in my PhD, I've worked towards this goal. So the first thing that I did was that I looked at how personalization is done in other domains, and I found 3 mechanisms that can be adapted to haptics. So one of them is simply choosing from a set of existing signals, for example, a set of vibrations. Another one is giving sliders or controls so that users can change overall characteristics of a sensation. So for example, changing brightness of a color or roughness of a vibration. And the last one is giving people tools to combine existing signals into a new one. So we did a user study on this, and we decided to go with choosing and tuning because these are the simplest and they provide fast and efficient control for end users. So then I went ahead to try to support choosing for a library, a large collection of haptic signals. And so the important thing here is that no one wants to spend 1 hour just to choose a vibration for their phone, right? So we need to provide easy and efficient access to these libraries. So to find an efficient way to access media libraries or vibration libraries, I looked at how people talk about haptic signals, and I took this basically messy, complex language space and turned it into a structure that can be used for organizing a vibration library. So I found that there are at least 4 ways that people talk about haptic signals. So sometimes people use sensation words, so they may say, this is rough, this is strong. And many times people use emotion words, so you may say, this is pleasant, I like this, this is annoying. Metaphors are also used a lot, so someone might say, this feels like drums, or this vibration is like a heartbeat. And finally, sometimes people think about haptic signals in the way they see themselves using it. So they may say that this vibration is good to tell me that the battery is low on my device. So we call these facets. A facet is a concept from the information retrieval domain, and it describes basically a set of attributes that are semantically related to each other. And so together they describe one way that people think about a phenomenon, in this case haptic signals. So here we have sensation facet, emotion facets, metaphor facets, and so on. So then I ran a user study where I gave a wristband to people. There was a vibration actuator on this wristband, and then they felt a vibration signal. I'm going to play a sound file that represents the vibration for you. Okay. So this is now very loud. And so they described this vibration. So this one was simple, short, pleasant. It was like poking, and it's good for confirmation or pause. Here is another example. Oh gosh, this is too loud. How do you? Okay, thank you. So this one, yeah, I think it's better. Yeah. So this one was long and bumpy. It's unique and pleasant. It's like drums, and it's good for encouragement. So in this way, I designed a library of 120 vibrations, and I collected users' descriptions for this library. And then I designed an interface to give efficient access to this library. So this interface is called VibViz. It's available on my website, and all of the vibrations are open source in case someone is interested to use them in their work. But now I want to show you a video of some interactions with VibViz. So VibViz has 3 main views, the sensation view, the emotion view, and then the metaphor and usage example views. And so if you hover over a vibration, it will start playing. And all of these three views are connected together, so they show the same set of vibrations. And there are these natural language filters on the side that people can use to narrow down their search. So I'll quickly show you how I would choose a vibration for my interval workout. So I didn't want it to be too fast or too rough. I thought it's good if it's lively and if it feels like a heartbeat. So in this way, I quickly narrowed down my search to a small set that I could go ahead and explore. So this is one way to use VibViz. We studied how people use this interface, and we found that people vary a lot. So some people use the sensation facet a lot, some people use metaphors, but overall, the majority of people tended to use the emotion facet. So VibViz is for choosing. It's kind of like these color swatches. It's discrete, so you cannot go in between colors. And I wanted to provide users with a way to also tune vibrations in a continuous space. So here the question is, what should be these high-level sliders? And then how would these map to the engineering parameters that we know how to control? So to answer these questions, I analyzed the data set that I had collected from people using dimensionality reduction techniques. And this gave me a number of continuous dimensions for each facet. So for example, for the emotion facet, our results suggested that 3 dimensions can capture the variability in people's descriptions. And these dimensions seem to be pleasant, how pleasant or agitating vibration is, how lively or boring it is, and how familiar or estranged the vibration is. So then I took these dimensions and used them as the high-level sliders. My analysis also gave me some hypotheses about how these would map to the low-level engineering parameters, such as frequency and waveform. Then I ran a user study to validate this emotion to engineering mapping. So our results suggested that there is a mapping between agitation and liveliness of vibration and the frequency and waveform of it, and another mapping between estrangeness and the irregularity and discontinuity of the vibration. So for example, you can see that the estrangeness mapping is not necessarily a linear relationship. Okay, so to summarize this work, in my PhD, I developed a suite of tools, choosing and tuning tools that are built on one underlying model. I think haptic facet is a good way to capture users' mental model for haptic signals. And future work needs to look at how these can be incorporated into various workflows and applications of people. So I'm going to come back to this at the end of my talk. I was honored to receive the Best PhD Thesis Award for this work, and as a result, I had the opportunity to revise my thesis and publish it as a book called Personalizing Haptics. Now I want to switch to another project that I did near the end of my PhD at UBC. And in this project, we were interested to crowdsource haptic evaluation. So in my PhD, I had to collect a lot of descriptions from users, and this was a very tedious process. So I wondered if we can use online platforms such as Amazon Mechanical Turk. So Amazon Mechanical Turk is this online website where anyone can go and upload a task, and then people from different parts of the world can complete this task for a small amount of money. So this gives us access to a more diverse population than what we normally have in lab-based studies, and also it's a cheaper and faster way to collect data. But the problem is that in haptics, we usually need to use hardware, and this hardware tends to be specialized. Even for vibrations, I used C2 tactor, which is higher fidelity than what we have in cell phones. So we asked, can we use proxies? So for high fidelity vibrations, we came up with 2 types of proxies. So low fidelity vibrations that can run on smartphones and visual icons. So to validate this idea, we took 10 vibrations with different characteristics. We created proxies for these, and then we ran studies in lab and Amazon Mechanical Turk to see whether they match. So for the vibration proxy, we used Android phones. And so for each vibration pattern, we created a pulse train using Android API to represent the same or a similar sensation to the original vibration. For the visual proxy, we explored colors, texture, and so on. And at the end, we came up with two types of proxies. One of them is, we called it baseline proxy. So this is the exact waveform drawing of the vibration. And this is usually what haptic researchers show in their talks when they want to show a vibration. And then we also have with emphasis, which we design using line properties such as the thickness and roughness of the line to show characteristics of the vibration. And then we ran the studies in lab on mechanical torque, and we found that proxies can communicate key features of the original vibration. We found that they were not perfect, so some of the properties such as the energy of the signal was not captured by any of the three proxies. But the good news was that the two proxies that we had specifically designed worked better than the baseline proxy, which suggests that if we work more on the design of the proxies, they can get better and eventually convey more characteristics of the vibrations. So in this project, we proposed the idea of proxies as a way to give experts and application designers access to a large number of end users. Okay, now I'm going to switch to the second part of my talk, which focuses on kinesthetic technology, and specifically on force feedback devices. So force feedback devices are robots that are controlled by human, and this is an example of them. This is Phantom Omni. It's basically a commercial haptic device. It's used in many different types of haptic research. And so you can see that as the user moves this device, she can feel forces from it that tells her that she's pushing on a button, she's going over a surface, or, for example, she's tapping on the surface. So the first project that we did here was that we wanted to know how novice application designers use force feedback hardware to create multisensory applications. So this work is done in collaboration between University of British Columbia, Hapley Robotics, and University of Waterloo in Canada. Right now we are revising our submission to transactions on haptics. So the scenario that we had in mind was simple. Someone wants to use haptic hardware to create a multisensory application. So from our previous experience, we knew that this process involves multiple components. They need to deal with the hardware. They need to set up the hardware or modify the hardware. They need to think about the interactions that they want to create. They need to program the device, and they might want to do some sort of user evaluation at the end. So we knew that this process involves lots of components. And it's challenging, but what we wanted to know is that with the lack of guidelines that we have in the field, how do novices tackle this process? What kind of challenges they have, and how can we support them? So we ran a user study during the Student Innovation Challenge at IEEE World Haptics, and the topic of the challenge was using haptic hardware to support learning in science, technology, engineering, and math. So creating a multisensory application for STEM education. So from the 13 teams who submitted a proposal, we selected 9 teams, and we sent them a physical package that included 2 low-cost hardware, API for this hardware, documentation for assembling the hardware and using the API, and also we gave them technical support through a Google Groups, and also they could contact us with email. Then they had 9 weeks to go and complete the challenge. And during these 9 weeks, we sampled their process. So at the start, we had their proposals. During the process, we distributed 2 surveys to them. At the end, they wrote a blog post. We talked to judges of the challenge who evaluated their outcome. And we also had a focus group with the student teams to understand their experiences and challenges. So this gave us a lot of qualitative data, a lot of interview and survey data, which we analyzed with a qualitative analysis method called thematic analysis. So what we did was that we transcribed all of the interviews. We also included all of the survey data. And then we went through each line of text and applied the descriptive code to explain what is the meaning behind what the participant is saying. We connected these codes to identify the overall patterns of meaning. And then we wrote lots of memos and comments to describe these patterns. So this was a an iterative process that started with the descriptive code and ended at the final writing, but we had to go back multiple times to revise our codes and look at the data again. And we specifically looked at two things. One was what kind of environments they created, what kind of choices they made. For example, what information they showed through the visual channel and what through the haptic channel. Also, based on the data that we had, we could create a rough timeline of the activities that they performed and their overall process for each team. So this analysis, based on this analysis, we identified 10 design choices that someone who works in the field of haptics needs to make to create a multisensory application. We also provided a detailed description of their activities and challenges that they have. So this gives implications for tools who want to support these novices. But the main thing that I want to mention is that we found that for supporting novices, we need much more than easy-to-use hardware and programming tools. We definitely need them. But a lot of times these novices struggled with the choices that they made. They sometimes made choices that was wrong. And so we think these tools should embed, so we need to give them access to good examples, but also these tools need to embed information about the design choices and the process. Okay. So the next project is what I did at Max Planck Institute, and this was in collaboration with University of British Columbia. And in this work, we created a collection of haptic hardware to support discovery of this hardware and also designing for this hardware. So this work is called Haptipedia. You can think Wikipedia for haptics. And it's resulted in a publication at CHI last year. We also had a workshop during Asia-Haptics on this work. So hundreds of force feedback devices have been invented in the haptic community, but most people don't know about these hardware. So even experts in the field know about one or a few of these devices, but they don't know about the full range of this hardware. And we believe this slows down the field, creates repetitions, and also limits people's ability to create new hardware or new experiences. But there are good reasons that people don't know about these. These are buried in the literature. Some of these are in the haptics domain, some of them are in robotics, and some of them are in HCI. So it's difficult to find these devices, but also it's very difficult to understand the engineering language of these papers for someone who is not from the engineering fields. Some of the early inventions are not even archived online. So they are essentially lost to newer generations of designers. So we created Haptipedia, which is a library of over 100 force feedback devices. And our goal was to support people with different backgrounds. So those with engineering background who care about forces, resolution, and actuators, and those with the interaction design background who may care about robustness of this device or how easy to program it is. So Haptipedia is available online at haptipedia.org, and you should feel free to go and explore it on your own. But I want to show you like some of its features through two scenarios that I've recreated based on what we observed in our user studies. So the first scenario is from an experienced designer. So this person was interested in creating an application for visually impaired people. And he already knew about some of the devices, some of the force feedback devices. So he explored devices that we have in Haptipedia. This is the device gallery view, and looked at some of the devices in a bit more detail. And he found one device that he already knew about, so used that as a reference or anchor point. And then went to the timeline view, and there he could see some other devices that are related to this device. And so through this exploration, he could find some other potential devices for his application. So after looking at the timeline view, he was also interested in devices that are easy to fabricate. So he went to the user experience view, sorted on devices that are easy to fabricate, and then went through like the highest fabricability devices. And through this, he could find some other devices for his application. So after finding a number of potential devices, the website gives the functionality of comparing them, comparing all of their attributes side by side to decide which one is the best for a particular use case. The second scenario is for a device designer. So this person had an engineering background, and she had already created a device that moves in a large space. So she was interested in the device output. So she went to that tab and filtered for devices that have medium and large workspace, and then went through devices that have high force output. She was interested to look at haptic master, which is an important haptic device, looked at some of the images for this device, and also the video of the CAD model. A mechanical engineer in our team has created CAD models for some of these devices, and this is a video that shows like how this device moves in space and what is the scale of the device. She could also look at some of the information that we have extracted for this device. So these are two ways to use Haptipedia, and you can go and explore it in different ways. But what I want to mention is the process that we create Haptipedia. So the process started with reviewing haptic literature. So we reviewed over 2,000 papers in the haptic venues. We also talked to lots of experts in the haptic community. Some of them were during demonstrations of Haptipedia during conferences, but we also had focus groups with these experts and hour-long interviews with interaction designers and device designers. And so through this process, we iteratively refined Haptipedia in the and created the format that you just saw. And so this project has resulted in several directions. One of these directions that I'll briefly mention is submitted to CHI this year. And so in this project, we were interested to use Haptipedia to better understand the mental model of experts. In Haptipedia, we have lots of devices, and each of these devices have a lot of attributes. So more than 54 attributes for each device, and we have extracted these from the papers on the devices. So we saw that people who have some familiarity with the field, they can easily find their way around and use this information. But people who are new to the field and they're just learning, this might be very overwhelming for them. So we wanted to know how people mentally categorize and make sense of all of this information. So previously, we had created Haptipedia based on the haptic expert literature and input from the experts. But in this project, we used Haptipedia to better understand the mental model of experts and then feed that back again into Haptipedia. So we ran a user study with 18 experts. So in the study, we had some background interview. They also rated their familiarity with these devices. But the most important part was a grouping task. Where experts group devices according to their similarity. So in our interface, they could drag and drop these devices, put them close together to show that these devices are similar. They could look at some of the attributes of these devices and the specifications of them. They could annotate the groups to describe them, duplicate a device to put it in multiple groups, and they could also flag the devices. So at the end of the process, we interviewed them to understand what is the meaning of these groups and what's the criteria they used for creating these groups. So we analyzed this data in two ways. We aggregated the grouping data from all of the experts, created a device similarity matrix, and then we applied clustering analysis to this to find the main categories of these devices and also their similarities. For the interview data, we applied thematic analysis to this and found 6 attributes that we call them Uber attributes. They are more semantic at a higher level than what is in the specifications, what specifications we have in Haptipedia. And then we use this information to redesign Haptipedia. So this is the gallery view that is now redesigned to show the expert categories. And then, for example, you can still explore it in the same way, change the size of the icons and so on. But we also show similarity of the devices. So here, each dot represents one device. and then they are grouped according to the expert categories, but you can also go over the device icons to see similar devices in the same category or in different categories. So the project also has resulted in several other directions. So right now, a PhD student with Catherine is working on designing a measurement setup where you can put a haptic device there and measure all of the movements and forces and torques from it, and we would like to use that to model and characterize the devices. We are interested in the long-term impact of Haptipedia on the community. Recently we did a longitudinal study on Haptipedia, and right now we are logging the website traffic on it. And since the start, we wanted to scale and maintain Haptipedia through community input. So right now we are redesigning the data entry and data flow for the Haptipedia so that people can enter new devices and they can edit information on existing devices. And so this was based on the results of the longitudinal study. So to summarize, I talked about mechanisms that enable end users to adapt their haptic experiences. I talked about facets as a way to capture the mental model of the end users, and VibViz as an interface that gives playful and efficient access to a library of vibrations. I talked about the idea of proxies as a way to give experts and application designers access to a large number of end users. I briefly mentioned the process and challenges that novice designers have to create multisensory applications with haptics. And I talked about Haptipedia, which is a library of haptic hardware, and it's designed based on haptic literature, and it helps us better understand the mental model of experts. And these projects address the two main categories of tactile and kinesthetic devices. Now, I don't know how much, I have some slides on ongoing and future work, but if people have questions, I can end here. So.
Yeah, well, we can do both.
Okay. Go ahead.
Would you consider doing the sound thing that you did here for a proxy?
That's a very good question. Yeah, I think sound is potentially could be a very good proxy. The thing is that for some of the vibrations, the sound file is a very good representative, and for some of them, it's not a very good representative. So I think similar to the visual proxy that we had, if we use the exact sound files, it will be kind of like a baseline, and we need to do more work on the design of the sound so that kind of like they better represent. At the time that we did this project, we felt that we had more expertise in our team in terms of visual design, but I think it's definitely an interesting area.
So it is about haptic display, right? And there is a different area which is haptic sensors for robots. Right?
Yeah, so the sensing. No, so kind of like the project that I showed you mostly work on kind of like the display and the design of the output. But for example, for kinesthetic technology, like the input and output are tightly connected. So you need to be able to kind of like analyze the input to design good output signals. One of the areas of future work and ongoing work that I'm working on right now is more on the analysis of the input data. Maybe I'll quickly just switch to that because it seems to be related. Okay, so basically one of the areas that I'm interested in working on is applications or use cases of haptics. And so right now I have two main categories that I have in mind. So one is using haptics for skill training and one for human-computer interaction. And I'll quickly switch. So for these, maybe I'll go back. So one of them is using haptics for surgical training. So in this project, this is a setup that we have at Children's Hospital of Philadelphia here. And here we are capturing the movements of the tools that novice surgeons make, and we are analyzing that data to be able to understand what kind of inefficiencies they have, what kind of like actions they perform, such as picking up the tool and dropping the tool. And so this is analyzing the motion data, the input, and we hope to be able to design kind of like personalized or adaptive haptic and multisensory feedback that corrects these actions. And then the other area is using haptics for in the area of human-robot interaction for children with autism. And here we are attaching touch sensors to the body of this robot, and we are analyzing. So my role is basically analyzing the data from these touch sensors to identify what kind of gestures people make. And so this is kind of like all in the area of analyzing the input from sensors, and then the next step would be how would display the feedback using haptic technology.
Back to the one of the earlier things you talked about, that we have facets.
Mm-hmm.
So it seems like you can think of the facets as forming a basis that spans space of whatever haptic rendering. Do you have an idea about whether, or how big is the space? Are you covering most of what is possible in the haptic space? Or other facets that you think should be there?
Mm-hmm. Well, that's a good question. I think at least we are missing another possible facet, which I didn't have the possibility to fully explore. And it seems that at least for vibration, sometimes people use sounds to kind of like describe the vibration. So you might say, this is like zzz, or like bump, 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 you know? So this kind of is interesting in a way, because then you can also use these sounds to create haptic signals in a way. But it's not an area that is not explored at all, and we don't know how much variation people have in kind of like using sound to describe these signals. But I think that's another possible.
I was thinking about the question earlier when you said the sound doesn't always capture things. And I was imagining one tactile sensation which can't be represented by sound, but very slow frequencies that are inaudible. Are those things that you consider those as potential haptic signals as well?
Yeah, so definitely, I think there are some signals that you are saying that they cannot be heard, but they can be felt.
Yeah, if you had a pulse, 10 hertz, you would feel it, but play it out with speakers, you're not going to hear that.
Yeah, that's true. Yeah, so I think, I mean, it would be interesting. I mean, it's still a tactile signal. It would be interesting to see what sound representations people have for that thing, you know. Because I think the exact waveform output is not necessarily a good representation. So for those things and for really high frequencies and things like that, yeah. And I mean, so this work is, so the haptic facets and the proxies looked mostly at vibrations, but there are other types of tactile signals, so it would be good to look at those things and maybe other representations come up for that.
So that's interesting. I'm really curious about. I looked at the Haptipedia, and it said that there was a grounded feedback devices. So I looked for my devices. There was 2 or 3 that I had, and they weren't there. And I think it's because they're not grounded. They are vibration based, but they're not grounded. So it seems like there's a disconnect in the sense that that's just the grounded ones, and all the things we're talking about here, which are vibrational senses, aren't necessarily. They can be partially on that, but there's
so it's a good question. So I think, Haptipedia, we narrowed down for now the focus to be on grounded force feedback devices. The vibrations, we mostly have so far looked at the range of sensations that they can create. So they are not about the hardware as much as they are about the output and the signals that they can create. I think in terms of Haptipedia, we are hoping that either us or someone else could extend this to other categories of haptic hardware. So for example, wearable devices, exoskeletons, and things like that. But I think, and I mean, it would be interesting to see how vibration actuators are used in different configurations, for example, in wearable devices and in different configurations. We didn't focus Haptipedia when we were deciding to narrow down the hardware to force feedback devices. We didn't work on vibrations because the actuators themselves, there doesn't seem to be a lot of variations among them. There is some variation, but not huge enough to be interesting. But I think in terms of configuring these vibration hardware into devices and getting input and output, I think it's definitely interesting. Yeah.